You ever stop to think about how a self-driving car spots a stop sign? Or how your phone just knows it's your face? We see things without even trying, but teaching a computer to do that? Well, that's one of the biggest challenges in AI. Turns out, your standard run-of-the-mill neural network is basically blind to images. Today, we're going to find out why and dive into the brilliant solution that finally gave computers sight.
So here's our game plan. First, we'll look at exactly why images trip up a standard AI. Then, we'll cover a really clever trick for beefing up our dataset. After that, we're going to take a page from Mother Nature's playbook, and finally, we'll see how all these pieces click together to turn a bunch of pixels into a real prediction.
All right, before we jump into the solution, we have to really understand the problem. So let's start with the big question. Why are images so incredibly hard for a standard AI model to get right?
Look, standard neural networks are amazing tools, don't get me wrong, but they have this one fundamental blind spot when it comes to visual data. They weren't built to see the way we do.
Okay, here it is. This is the heart of the problem. A normal neural network needs a simple, flat list of numbers. So what do we have to do? We have to take this nice, structured 2D grid of pixels and just flatten it into a long line. See that middle pixel? It used to have neighbors all around it. Now it's just a number in a long, meaningless sequence. And just like that, we've completely destroyed the image's structure, the very thing that tells us it's an image in the first place.
And this flattening leads to two, frankly, huge problems. First, you lose all those spatial relationships. The network has no idea which pixels are next to each other anymore. So things like edges, corners, textures, gone. It can't see them. Second, you get what's called a parameter explosion. A tiny 200 by 200 color image suddenly becomes 120,000 inputs. This makes the network gigantic, incredibly slow, and really prone to something called overfitting, where it basically just memorizes the training pictures instead of actually learning what's in them.
Okay, so standard networks are clearly not the right tool for the job. But before we get to the new architecture, let's talk about a super powerful technique that makes any image model better. It's especially good at fighting that overfitting problem we just talked about.
The technique is called data augmentation, and the idea behind it is so simple it's brilliant. If you don't have enough data, just make more. We're going to artificially grow our training set and, more importantly, make it way more diverse by creating slightly modified copies of the images we already have. Check this out. Instead of just showing our model one single perfect X, we're going to show it that same X but scaled up, shifted over, and rotated a bit. This teaches the model to generalize, to learn the idea of what an X is, not just that one specific version. That makes it way more effective out in the messy real world.
And there are so many ways to do this. You can rotate the image, flip it, shift it around, shear it, zoom in. Every single one of these simple changes creates a brand new training example for our model, and it costs us basically nothing.
Now here is a really important pro tip right from the source material. Data augmentation is for training and only for training. You use it to make your model smarter, more flexible, but when it's time to actually test how well it performs, you have to use the original untouched test images. No cheating.
So, if standard networks are out, what's the answer? Well, the big breakthrough came from looking at the single best image processor on the planet, the human brain.
This diagram shows the amazing journey information takes from our eyes to our brain. You know, seeing isn't just one single event. Our brain's visual cortex actually processes what we see in layers, building up understanding piece by piece. And this exact step-by-step process is the blueprint for what we call convolutional neural networks.
It's really a beautiful system. When you look at a face, the very first layer of your visual cortex, V1, doesn't actually see a face. It just sees simple little edges and lines. Then, the next layer, V2, takes those lines and combines them into simple shapes. V4 starts putting those shapes together into more complex things. And then, finally, a high-level area like the IT cortex puts it all together and goes, oh, that's my friend's face.
And that is exactly what a convolutional neural network, or a CNN, is built to do. It's an artificial system designed to copy that same layered feature-detecting process that nature spent millions of years perfecting. It lets the machine learn to see in a way that's remarkably similar to how we do.
All right, so we've got the inspiration. Now let's get into the nuts and bolts. We are going to zoom in on the absolute heart of the CNN, the convolutional layer. This is where the magic happens. This is the part that actually does the seeing.
So the secret weapon of this layer is something called a kernel, or you'll also hear it called a filter. The best way to think about it is like a tiny, specialized magnifying glass. It's just a small grid of numbers, and its only job in life is to slide across the image and look for one specific thing. Maybe it's looking for a vertical edge, or a sharp corner, or a patch of a certain color.
And the process it uses is called convolution. It sounds fancy, I know, but it's just a few simple repeating steps. The kernel lays on top of a patch of the image. It multiplies its own numbers with the pixel values right underneath it. It adds all those results up into one single number, and it puts that number into a new grid we call a feature map. Then it just slides over one spot and does the exact same thing again and again and again all across the image.
And check out the result. Here we have a kernel that's designed to find edges. As it scans the image, the feature map on the right lights up everywhere it finds one. We've successfully pulled out or extracted a low-level feature from the image, just like the V1 cortex in our own brain.
And what about color images? No problem. A color image just has 3 channels, right? Red, green, and blue. So the kernel we use also has 3 channels. It just processes all 3 color layers at the exact same time to create that feature map. The logic is exactly the same.
So how does this all come together? We've got these convolutional layers that are great at finding features, but how do we use that to go from a raw image, say a chest X-ray, to a final answer like pneumonia or no pneumonia? Well, here's the whole blueprint of a typical CNN. You can really think of it in 2 parts. Over on the left, you've got the feature extraction part. That's where we stack up a bunch of these convolutional layers, and each layer learns to spot more and more complex features. Then all of that rich information gets flattened out and fed into a standard neural network on the right, what we call the classification part, and that's what makes the final call. So let's do a quick recap of the big ideas here. Number 1, standard neural networks fail at images because they flatten them and destroy all the important spatial info. 2, we can make our models way more powerful using data augmentation. 3, the whole idea for CNNs is inspired by the amazing, layered way our own brains process vision. And finally, 4, the heart of it all is that convolutional layer, using those little kernels to scan an image and build feature maps.
You know, this fundamental understanding of how a machine learns to see, it's the key that unlocks everything from spotting diseases in medical scans to helping self-driving cars navigate a busy street. You now have the core concepts you need to understand any of them. So the only real question left is, what are you going to build with it?